Hello guys, welcome back to Maison African Motives. Still working on engineering science and working on stress and strain. We are going to be focusing from the question paper of November 2022. In this case, we were given the question on question number 6, where we are given the first part 6.1 to state Hooke's law and Young's modulus of elasticity in this case, which is 3 marks for that. All right. So here I'm having both presented as the Hooke's law states that within the elastic limit of any body, the ratio of the stress to the strain produced is a constant. So that is what you have for the Hooke's law. And this constant is called the modulus of elasticity of material. The length modulus of elasticity is called the Young's modulus. So that is what you're given in this case, and we've got 3 marks for these definitions. All right, the other part of the question, which is on 6.2, we are now given that the following readings were obtained from a tensile test. Take note when you are dealing with the tensile test of a bar, we have got these, the load in kilonewton and the extension, which is given in millimeters. The gauge length is in millimeters. The diameter is in millimeters. So these dimensions that you see here, they are in millimeters. And the force, which is our load, is given in this case in kilonewton. All right. So the first part that you're given, so we've got readings, that's 1, 2, 3, 4, 5, 6, which corresponds with this table that you're given. So you're given to copy and complete the stress table of the above information in exactly the following format. So here, we have got our stress on the table. We are given the stress and we are given the strain. So these are the two that are given. The stress being measured in megapascals, that is our load, and the strain, the answers are supposed to be as times 10 to the power of minus 4, times 10 to the power of minus 4, like that. Okay, so that is what you're going to have in this case. Okay, so the first part is how are we going to obtain these values? Where are we going to have these values from? Okay, so here our stress, which is obtained from the formula. So remember that stress can be obtained from the formula of force over area. So here we are going to have our stress as force over area in this case, and our strain can be taken from the extension that we are given, which is the change in length, our extension over the original length in this case. All right, so this is our extension, which is our x. All right, so we are supposed to have these values in millimeters. So the gauge length, which is our original length, if we divide by 100 by 1000, so that we convert to millimeters, this is going to be 0.056 in meters. The original diameter, if we convert again to meters, divide by 1000, this is going to give us 0.01127 in meters. So this is your original diameter, which is going to give us the area. Since here we need the area, all right? So we need area from the diameter, okay? So that means we can calculate our area. And this is the area that you're going to use for your calculations, all right? So let's just have our area from this information on top here. Let's just have our area. So remember that our area is given as pi over 4 times d squared, or id squared over 4, which is pi over 4 times the diameter, the original diameter here of 0.01127 squared. All right, so this is going to give us the area, which is going to be 9,976, if you round off to 3 decimal places, times 10 to the exponent of minus 5 in square meters. All right, so remember, we use the diameter in meters, so our area is going to be in square meters in this case. All right, so having this area, I want us to consider this, what you are going to do. The first part here, our stress, remember, we force over area. So here we've got 0, we've got 0. So meaning to say, there is nothing that you're going to have on the first part here. This is just going to give us 0. This is going to give us 0. So I'm going to explain from the second part. So this is 1, 2, up to 6. So we've got 1, 2, 3, 4, 5, up to 6 also. Okay. So on the second part here, we are given the load and the extension, the load that is our force in kilonewton. So in order for us to calculate the stress, we said stress is equivalent to the force over area. So this is going to be the stress of the first part, the second part this now. So this is the second part. So we are going to write this as the stress for the second part is going to be the force that is on the second part here. We are given the force on the second part, which is our load of 2,5. So you're going to use the force which corresponds with the stress that you're calculating over the area. The area is the original area. It does not change. You use this original area, okay? So that means we are going to have the force which is given as 2,5 kilonewton. So that's 2,5 times 10 to the power of 3 kilonewton, 2,5 times 10 to the power of 3 over the area, the one that we calculated before. We calculated our area as 9,976 times 10 to the exponent of -5. So here we are going to obtain our stress, which is measured in megapascal. So on your calculator, you are going to obtain this value 2506.0144 0.35 pascals, like that. So in order for you to convert to take note, guys, this is megapascal that you want to convert to, whereby megapascals means times 10 to the exponent of 6. So for you to convert to the megapascal, which is the 10 to the exponent of +6, you multiply by the inverse, which is 10 to the exponent of -6. So this you are going to multiply by 10 to the exponent of -6. By doing so, you are converting your answer direct to megapascals, which is going to be 25, on your calculator, you're going to see 25,0601 and so forth. So that answer that you see, it is now in megapascal. So that is going to be 060 megapascal, which is just 0.6 megapascal. So take note, we are given this is supposed to be in megapascal. So the answer that we need is the 25.06, which is in megapascal. So 25.06, take note, here it is in megapascal. That's why we have to convert. So we need the answer there, which is 25.06. So this is going to be 25.06. You do the same thing for the 3, for the 4th, and so on. The same with the strain. Okay, let's move on to strain and see what you're going to do. On the strain, we are going to use the second one, which means you're going to use the second part on your extension. This is the extension that you're going to use. Remember what I said, that the strain is taken from the extension over the length, the original length. So here, that means the strain that is going to affect the second part, we are going to use the extension for the second part over the original length. So here, the diameter, the area does not change. The same thing with the original length. These two do not change. What is changing is the force and the extension. And what you need to know is these extensions, they are given in millimeters. So this is 0,0056 in millimeters. So we are going to have our extension of here we are going to have our extension 0,0056 millimeters. If you convert to meters, that's times 10 to the power of -3 in meters over the original length in meters. Remember, here our original length is 0,056 meters. So we are going to use this in meters over 0,056 in meters. Meter and meter cancel. So we are going to obtain our answer as 1 times 10 to the exponent of -4 from your calculator. So this is what we need. The answer is supposed to be times 10 to the exponent of -4. So here we are going to take this answer here already. The exponent of -4, we can see it here. So our answer is going to be 1. This is the answer that you're going to write on your table. Already, it's already multiplied to 10 to the power -4. So you take the 1 that is multiplying to 10 to the power of -4. So this is going to be a 1. So that's how you're going to calculate these values throughout till the last part. All right. So meaning to say, on the third part, we are going to calculate the stress the same way we calculated here. We are going to use, instead of F2, we are going to use F3. So if we are to calculate for the third part, we're going to use F3 over the original area. So our F3, you multiply by 10 to the power -3, just like the previous part, okay? Then convert to megapascal, just like the previous part. You multiply by 10 to the power -4. That's what you're going to have in megapascal. So this is going to give us 20. All right, so this is going to be 98, okay? 98, 937. All right, you do the same thing for the strain. The strain, just like what we saw here, is going to be the change in length over the original length. So the change in length here is going to be x3 over the original length. So you do that, your answer is going to be 4, you're going to obtain something like this, 4,393, something like that, times 10 to the power of -4. So what we already need is 10 to the power -4. So our answer is going to be this part, 4,393. So that's what you're going to do. You multiply everything just like what I did on the first part. All right. So this is going to be 4,393 and so on and so on. All right. So you're going to fill in your values with the second part. The fourth part, again, you use your F3, your F4 in this case, just like the other part. This is going to give us 173, 115. Then the strain is going to give us 8, 143. Okay, the 50 part, which is the same, this is going to give us 247, 594. And here you must be careful. When you calculate the strain for the 50 part, your strain is going to be like this. On your calculator, your answer is going to be 1,189, something like that, times 10 to the power of -3. But here, our answer is supposed to be times 10 to the power of -4. So how do you convert this answer that is going to be displayed on your calculator to times 10 to the power of -4? You multiply by the inverse. The inverse of -4 is going to be power of 4. So you multiply by 10 to the power of 4. The moment you do this, your answer is going to be 11,893, something like that, okay? Which is now times 10 to the power of -4. So automatically, you have converted your answer to times 10 to the power of -4, but you multiply by the inverse of where you are converting to. You are converting to the power of -4. The inverse is going to be to the power of 4. That is the one that you use to multiply. This answer that you get will be times 10 to the power of -4. So this is the answer that we want, which is going to be 11, so you're going to obtain something like 11,893. All right. The 60 part, you calculate your stress. Your stress is going to be direct 321,772 if you convert megapascals. And your strain, just like this part, you are going to obtain again 1,6 times 10 to the power of -3. But you want to convert to 10 to the power of -4, so you multiply by 10 to the power of 4. So this is going to give you 16. The 16 that you get is going to be to the power of -4 automatically. So your answer there is going to be 16. All right, so that is how you're going to fill in this table by using the formulas that I stated here for the stress and for the strain. So if you're dealing with the 50 part, this is going to be the strain for the 50 part. You're going to use the extension for the 50 part over the original length. The same with the stress. For the stress of the 50 part, you're going to use the force that corresponds to the 50 part over the original area, and so on and so on. All right, so these are the typical questions that you might be given. So typically, each part is going to carry half mark, half mark, half mark, and so on. All right, so that is what you're given in this case. Let us move on to question 6.2, 6.3. All right. A steel bar is now given here, which is actually loaded by a tensile load F. So this is our tensile load F, as shown in Fig 1. This is the Fig 1 below. And it causes, take note, guys, when you are reading the question, understand the information. It causes the maximum stress. So wherever you are given the maximum stress, here we are given the maximum stress of 120 megapascal. It means it was taken from the minimum area. Take note that, remember what we said from the previous calculation, that stress is equivalent to force over area. So in order for you to obtain maximum stress, this must be as little as possible. So the area is supposed to be minimum. So that is what you're supposed to note in this case. Okay, we are also given the Young's modulus, which is E, which is equivalent to 200 gigapascal. And also we are given to calculate the total change in length, which is xt. So you can just write this as xt. So asked to calculate the total change in length, which is xt. All right, which is the extension, the total extension in this case. All right. I want us to consider something here. This part we are given here the diameter of the first part. So this is our first portion, the second portion. So here we have got the diameter, which is 40 millimeters. So this is our diameter 140 millimeters. If you convert to meters by dividing by 1000, that's something like 0.04 in meters. Same thing here, we are given the diameter of the second part here, which is 30 millimeters. So if we divide by 1000, that's 0.03 in meters. All right. These are the length that you're given. So this is our first length from this point to this point, which is 165 millimeters. If you convert to meters by dividing by 1000, that's 0.165 meters. Same with this part, we are given L2, which is 0.16 in meters. Okay, so how can we obtain a total change in length? Take note, there are so many formulas. From your formula sheet here, there's this formula that I want you to see, and I want to play around that formula. Most of us, we neglect this formula, but it is the best formula whenever you're dealing with the change in length and you're given all this information here. We are given that E is equal to FL over area times the change in length, which is the extension. I'm going to take this formula and play around this formula. You're going to see this. All right, so here we are given that, okay, let me take it this way. We are given that from the formula, E is equivalent to FL over area times the extension. If you are to cross multiply here, we are going to have EAX is equivalent to 1 times FL, which is FL. Remember, we want to make LX the subject. This is our extension. So you can divide by area times E, or by AE by EA, whatever that you want here. So you're going to divide by AA by EA like this. So this is going to give us the extension, which is force times length over E times A, which is area times the E, which is our Young's modulus in this case. So this formula can actually be used to calculate any part of an extension. But in this case, we are given to calculate the total extension, which means from the first portion here, there is an extension. The second part, there is an extension. So this is going to give us the total extension from the formula. So you're going to have our formula as the total extension is going to be x1 plus x2. But remember that an extension is taken from FL over AE from this formula that we manipulated. So meaning to say, from the first part, there is the length and area that we're going to have. So this is going to be F times the length of the first part over the area of the first part times E. The force is not going to change and E is not going to change. The second part also, we're going to have FL2 over area 2 times E. where F and yet the Young's modulus do not change. So this is the formula that you can use to calculate XT at once. Or you can even factor out F over E, because F over E does not change, F over E does not change. So if we factor out F over E, we are going to remain with the length over area, which is L1 over area 1, plus length 2 over area 2. So this is length 2 over area 2, like this. And also we know that the area can be calculated from the given diameter. So this is going to be F over E. And here we're going to have L1 over the area, which is pi d squared over 4. So the diameter is the first diameter that you're given, plus L2 over the area, which is pi d squared over 4. And this diameter is the second diameter that you're given. So this formula can give us direct our change in length. Yes, we can calculate the first part, we calculate the second part, but that is going to affect our answer because you are keeping on rounding off your answers. Instead of having this, we can obtain the exact value. Yes, if you check your memo, sometimes they work out the first extension, the second extension, then they add, which is fine. You can do that. You can actually use these formulas here. You calculate from this formula, you calculate the first extension, which is your x1 from this formula, your x2 from this formula, then you add, which is one and the same thing. All right. So what you see, if you can check here, we do not have F. All right. We do not have F. The other part, we have the diameters and everything, but we do not have the force. So where are we going to have the force? Remember what I said here. We are given the maximum stress. So from the maximum stress that we are given, we know that the maximum stress is taken from the minimum area. And the minimum area means we are going to consider the minimum diameter, which is this one. This is the maximum, this is the minimum diameter. So we're going to consider the last part to calculate F. So here, if we manipulate F to be the subject, F is going to be equal to 1 times F is F. That's stress times the minimum area. So you're going to have the maximum stress times the minimum area in this case. So that is what you're going to have to calculate F. So that means our F is going to be, remember area we said is pi d squared over 4. So this D is the minimum diameter, which means you're going to use D2. That is our minimum diameter. From the two diameters that we have, the least diameter is 0.03. So here we're going to have the maximum stress of 120 megapascals times the area, that is pi times the minimum diameter, in order for us to have the minimum or the least area in this case. So it's minimum or least area, which is 0.03 squared over 4. So this will give us the force. So in this case, we are going to obtain a force of 84,000 actually. So 84,000. So this is going to be 84,823.002 Newton. All right. So this is the force that we have in this case that is applied at this point here. So having this force, we can substitute everything into the formula. Remember the formula that we ended up with here, that we can calculate xt from this formula, that our xt, which is the total extension, is going to be force over the Young's modulus, the force of 84,823.002 over our Young's modulus, which is 200 gigapascal, which is that's our E here, 200. So you're going to have this as 200 times 10 to the exponent of 9 for gigapascal. All right, that's everything into length 1, the first length from our diagram here, the first portion here. Our L1 is 0.16, so we're going to have 0.165. That's our length here, 0.165. So everything is over the area, which is pi d squared over 4. So it's going to be pi times the diameter of the first part. The diameter of the first part in this case is 0.04. So that's 0.04 squared. So we're going to have this as 0.04 squared over 4. So this gives us the area of the first part, okay, plus L2, which is the length of the second part from our diagram here, the second part is having a length of 0.16 meters. So you're going to have 0.16 meters here. All right, so that's 0.16 meters over the area, which is pi d squared, the second diameter, that's d2. So it's going to be pi times, this one, we calculated it if you check here when we were calculating the force. So that's our diameter 0.03. So you're going to have 0.03 on this part. All right, so this part is going to give us the total extension of everything. If we can be able to manipulate your formula like this, you do not have problems. All you need is to just substitute your values from the manipulated formula, or to know this formula. Actually, it is very, very possible for us to know this formula. Okay, so if you are to calculate from this, you're going to obtain something like 1,1, 1,5, 168, and so forth, which is 17 times 10 to the exponent of -4 in meters. All right, so that's our extension. In this case, we are obtaining this in millimeter and in meters times 10 to the power 4 meters. You can convert to millimeters if you want, or you can just simply write as it is like this. That is our final answer, or our final consideration in this case. All right, so that was our question, guys, on stress and strain. So this is very, very important. 8 marks for that, to calculate the change in length. So like I said, there are so many ways. We're going to have this question in another way. That is the best way that I can do. I'm going to have this in another way so that you can also understand either ways on calculating the total change in length, or the total extension for a given combination of bars that you be given like this. All right, so that's it, guys, from Amazon African Motives, working on engineering science and for till we meet again.